Hello everyone and welcome to my 2021 Eusipco presentation. My name is Juan Cervino and the title for today is Multitask Supervised Learning via Cross-Learning. Let's begin by breaking down the title of the paper. What is supervised learning? Supervised learning is one of the traditional problems studied in the area of statistical learning theory. The interest in the subject stems from the fact that plenty of daily life problems can be posed as a supervised learning problem. Nowadays, supervised learning is an active area of research, particularly in the subfields of self-driving cars, classification, and recommendation systems. In order to formulate a problem of this type, we need to collect a dataset of labeled samples that we assume they come from the same unknown distribution. The problem is thus to obtain a function that predicts the label on unseen data from the same distribution. The problem is challenging as we don't know the distribution where the samples come from. In this particular paper, we will restrict our attention to functions that belong to the class of neural networks due to their outstanding generalization capabilities. Now, what is multitask supervised learning? In short, it is similar to supervised learning in that we have labeled samples from a distribution, but now we have several different distributions. By task, we refer to a distribution where different sets of samples are obtained. The objective now is to find a function or a set of functions that perform well on all the tasks. The challenge in multitask supervised learning arises as we do not know the distributions nor the relationship between the distributions of each task. The problem of multitask supervised learning has received close attention, and there are several solutions that have been presented. Some approaches focus on learning sparse representations shared across multiple tasks. Some other approaches assume that the task relationships lie on a manifold and they seek to learn the manifold representation. From the works that do not make assumptions over the task relationships, some papers focus on learning them through clustering. In the context of support vector machines, some related works bound the pairwise distance between the classifier weights. From a fairness perspective, some works look for Pareto optimal solutions between tasks. In this paper, we present cross-learning as a solution to the multitask supervised learning problem. Our objective is to obtain n functions, one per task, that stay close in the optimization space. To this end, we introduce a central function and a measure of centrality epsilon, and we optimize over the parameters of the functions. Cross-learning is a trade-off between learning task-specific functions and learning a single function, ignoring the task dependency from data. As mentioned before, in this paper, we will consider functions that belong to the class of neural networks. Let's make a couple of remarks about over the cross-learning problem. If we set epsilon to 0, then we will have a single policy for all tasks, as the constraints will collapse into only one set of parameters. This is equivalent to mixing all the data sets and ignoring their task dependency. In the literature, this has the name of consensus. If we set epsilon to infinity, then the constraint will always render inactive, and the central policy undetermined. Thus, there is no cross-pollination and tasks are learned separately. This receives the name of agnostics. In order to illustrate the benefit of cross-learning, let's look at a simple estimation example. The problem here is to estimate the center of two Gaussian distributions on the real line, which we assume are epsilon 0 close to each other. Note that epsilon 0 is unknown to us. We will be given m samples of each of the two distributions, which we will assume have the same variance. Let's begin by the consensus estimator, which corresponds to only one estimator obtained by setting epsilon equal to 0. In this case, we will obtain a bias estimator that will have twice as many samples as the agnostic estimators. On the other hand, the agnostic estimators will be unbiased, as we will estimate the means separately. However, only samples from the same distribution can be used. Cross-learning allows us to use all the samples while being able to obtain two different estimators. In what follows, we will show that cross-learning obtains a better estimation error than both the agnostic and the consensus estimators. In the figure, we can see the expected mean square error of the classifier with respect to epsilon. As seen in the image, cross-learning estimator can outperform the agnostic estimator by a factor of 3/4 when setting epsilon equal to epsilon 0. What is more, we can show that there always exists a value of epsilon such that the cross-learning classifier is better than consensus. Thus, in this particular illustrative example, we can show that cross-learning is better than both the agnostic and the consensus estimators. To obtain the solution to the cross-learning problem with neural networks, we resort to a projected gradient descent algorithm. Iteratively, each of the n policies are updated by taking steps in their task-specific domain. After each gradient step is taken, we project the policies so as to keep them epsilon close to the central policy G. Neural networks may have millions of parameters, rendering the implementation of the projection PC challenging in practice. It may be challenging to optimize the parameters of a neural network due to their large dimension. However, we can exploit the fact that only one constraint is added per task, which translates into one real value multiplier per task. To take subgradients of the Lagrangian, we only need to calculate the inner products between the functions once, alleviating the computation burden of working on the primal domain. Note that as the projection is a convex problem, the primal variables can thus be recovered. We benchmarked the cross-learning algorithm in a classification problem with real data. To do so, we consider the Office Home dataset, which was curated by Benka Teswara in the paper Deep Hashing Network for Unsupervised Domain Adaptation. In this case, we have 65 different categories and n different domains or tasks. Each domain shows a picture in a different setting. So for instance, if we consider the case of the label alarm in the task or domain art, we can see an artistic representation of an alarm. If we consider the alarm in the task clipart, we can see a clipart representation of the same alarm. In product, we can see products as shown for sale, and real world represents real world pictures of the object in display. We used neural networks for the architecture, which were based on AlexNet and have roughly 5 million parameters. In this case, we are able to see the empirical manifestation of the claims we put forward, as we are able to achieve a better classification accuracy using cross-learning than using both agnostic and consensus classifiers. The largest margin of improvement corresponds to the agnostic classifier in the domain of art, where the accuracy almost triples. Note that this is expected as art is the domain with the smallest number of samples. We can also conclude that there always exists an epsilon that outperforms both the consensus and agnostic classifiers. If we plot the average accuracy over all tasks with respect to epsilon, we can see that the cross-learning classifier outperforms both the agnostic and the consensus classifiers. In this image, the agnostic accuracy corresponds to 24%, which is not plotted in the figure. Even though we do not know the relationship between the images, we know there exists a relationship, as combining all the images, which corresponds to consensus, is better than ignoring the task dependencies, which corresponds to the agnostic classifier. To conclude with, in this paper, we introduce a cross-learning framework tailored for the multitask learning problem. We derive intuition on the advantages of formulating this optimization problem on the parameters, but showing that cross-learning is expected to outperform both the agnostic and the consensus approaches on an illustrative case. To implement the cross-learning problem in neural networks with millions of parameters, we derive a dual domain algorithm. Finally, we showcased the advantages of cross-learning in conjunction with neural networks in a real-world example. If you made it this far, thank you so much. Please don't forget to take a look at the paper and let me know if you have any comments.